So my purpose today is not so much to present to you a completed research, but more to inspire you to start some thinking along these lines. I'm involved in a number of aspects of this AI and SE thing, both from Raytheon perspective and in some standards committee with SAE and INCOSE and so forth. So we'll try to be a little bit inspiring. There we go. All right. Well, I grew up in a different part of the U.S., but working with Raytheon missile systems, I spent a lot of time now in Tucson, so I found out things are a little bit different in Tucson. If you're not familiar, this is what we call a river here in Tucson. This is exactly what that is. This is what we call a lawn. And they all pretty much look like this. This is a tree, by the way, in the Tucson language system. And this is a parking lot. And we have some of these out there. We keep old airplanes in the desert, right? Because they last a long, long time when you park them in the desert. That's why they're all parked out there. This is a bike ride. We call it a bicycle ride. This is the Tour de Tucson. 10,000 cyclists come out every year and ride around Tucson. And this is what we call September. 40 degrees in Tucson. That's right, 104 for those of you who speak Fahrenheit. All right, well, so when we first started using computers, this was one of the first computer interfaces I used. Anybody remember these? So this is a teletype machine. We had to adapt to the way the computer wanted to interact with us, didn't we? And how this computer wanted to interact is one key press at a time, one character at a time. It would give us back one character at a time, we'd give it one character at a time, or one little paper tape at a time, right? Then later on, we have the terminal that you mentioned, right? The green screen terminal, where we would give the computer the information one screen at a time, and then it would give us back all the errors right on that screen we'd have to deal with. So we were adapting to the limitations of the computer, right, of the system. Now, Moore's Law, someone mentioned that earlier today. There's some debate about whether Moore's Law is continuing, or is tapering off, or is changing. It seems to be continuing, at least in the larger sense of compute power per cost, right? Because the way compute power is being calculated is changing, right, to GPUs and things like that. But anyhow, somehow the capability of computers per cost, per dollar, or per euro, right, is still increasing dramatically. So the question is, what are we going to do with all this power, right? Can we make systems better using all this power? So is this 25 years of progress? So you may not recognize the system on the left. This is from the probably 80s. It was a lovely little system called Q&A, where you could program your little database and retrieve records and all this stuff, right? And you had to enter the information into the screen field by field, just the way the computer wanted it, and the computer was limited. Now, of course, today, in 25 years of progress, we now have Amazon.com with all of their AI, and we enter this information the same way, one field at a time, okay? So has it gotten smarter? I don't know, maybe not so much. We still enter it the same way. You ever try entering something a little bit wrong? It just says, invalid, sorry, try again. You know, you'll have to try again. So you try the same thing again. Well, that's not what it meant. It didn't not try it again. It should say, invalid, try something different, right? It had to be that, okay, try again. Anyway, okay. So now let's talk about chess for a moment. Anybody who's a fan of chess or plays chess? So Garry Kasparov wrote a wonderful book just a couple of years ago looking back on his time as the world chess champion. And the book was called Deep Thinking. And Kasparov was interesting because his reign as the world chess champion spanned the 20 years when computer chess went from nothing to a competent player to a champion to even beyond. Right? So he watched all this and he kind of embraced it, he kind of explored it, and of course his famous match with Deep Blue from IBM is pictured there, and that's a famous thing where he had 2 matches in 2 years. He won the first match, and then the next year he lost the next match. He still won some games, so he's right on the edge, right, of the computer being able to beat the best living chess player at the time. But Kasparov says a number of interesting things, and I'll just underscore this one here. That he says, with so much power being brought by the computer, what we have to do now is find a refuge in our humanity. And it's about the qualities that we have as humans that machines, he claims, will always lack. Now, we could debate whether machines will always lack these qualities, right? Who knows, right? But for now, they lack intuition, they lack creativity, they lack strategy, things like that. So we have to define the boundary then where there's going to be this new collaboration, right? Where we do what we're good at and the machines do what they're good at. See, Kasparov invented this thing called advanced chess. Have you heard of this? So advanced chess is a tournament where who can enter the tournament? Human, or a machine, or what? a team, right? A human plus a machine. And it's the human plus the machine that tends to win those tournaments. Because the human is not the best chess player human in the tournament, but the combination of the human and the machine beats all of the other humans and all of the other machines. This is very interesting, right? So somehow it's that synergy. So what is the form of that, right? So if we start now exploring more what we mean by intelligence, and that's kind of where I'm going with this, is one way of thinking about intelligence in one narrow way is vocabulary. And so we see human beings, of course, develop a vocabulary, and it grows throughout their age and tapers off, of course, as you would expect, right? So, we meet, why is vocabulary important? Well, Wittgenstein, you're familiar with, we'll give you a little philosophy here, philosophy of language, right? Wittgenstein says it's not about the definitions of words, it's about the usage of the words. That what a word is its usage in language, right? So as we learn more words, we're able to converse more. That's important, and it's important that it grow. It's natural that it grow in an intelligent system. The only intelligent system that uses language that we know of right now are humans, right? Animals in a very, very limited way. The Hi, How Are You test refers to a conversational system I was asked to test a few years ago. And of course, you're confronted with a conversational system. What's the first thing you type? Hi, how are you? And it said, I'm sorry, I don't understand. And I can, now that I know much more about neural networks than I did and how a system like that would be programmed, I understand why that happened, right? And it makes sense why that happened. But still, how old does a human have to be to produce a sensible response to how high how are you? I don't know, 1 year, less than 1 year? Something like that, right? So we're not there yet in terms of seeing systems as being able to grow and develop and be intelligent the way we humans think of intelligence and the way we interact with intelligence. Or as John McCarthy said, as soon as it's AI, as soon as it works, as soon as it's implemented, we don't call it AI anymore. See, chess, we have a hard time thinking of Deep Blue as AI, don't we? Because it worked. And guess what? All it could do was play chess. It wasn't intelligent, it couldn't converse, it couldn't do anything but just play chess. And if you knew how Deep Blue worked, you would be surprised at how simplistic its structure is and how it actually played chess. It played the entire endgame, for example, from a table. It played all its openings from another table. So it's another story. Now, if you like movies, have you seen this one? A movie called Her, starring Joaquin Phoenix. So watch the movie, or if you don't want to watch the whole movie, just go on YouTube and search Her installing Samantha, just like that. And you'll see this wonderful scene about his first interaction with this new OS, they called it, operating system, right? And but she says very human things, and it's very interesting how the makers of this movie portray an intelligent operating system. She says, hi, how are you? Well, she says, hi, how are you? It's just like that, right? Or she says, it's very nice to meet you. I have intuition. She says things like this. They're very human-like, intelligent-like things. She says, I looked through your email. Most of them we can throw away. Let's keep 86 of them. Very interesting kind of interaction as he develops his relationship, as you will see in the movie, with this OS. All right. So we still see a large gap now. If we paint this gap between what we have today, Google search, Amazon, Echo, all those things, and what we see in the sci-fi future. Anybody else like sci-fi? You see the portrayals of these intelligent systems, the Enterprise, the Samantha, Jarvis. By the way, any Star Trek fans here? Have you ever noticed that the computer on Kirk and Spock's Enterprise was much more advanced than the computer on Picard's Enterprise, which of course takes place 200 years later in Star Trek? Why is that? Well, because the original series was made in the 60s. And in the 60s, we all thought computers were going to be able to interact that way and draw conclusions and correlate information and do wide open queries and things like that. By the 80s, we were not so ambitious, and so that computer acts much more modestly, and is more straightforward, more realistic. It's very funny to watch those from that perspective. So what I want to say is what's going to bridge this gap is the engineering of intelligent systems. And that's the challenge, I think, that confronts us as systems engineers. Not designing algorithms, not programming AI, but designing intelligent systems. See how that would be something different. So what do we mean by an intelligent system? Well, intelligence, from the dictionary, is the ability to apply knowledge and skills. So that's not a very high bar, is it? Does Deep Blue have intelligence? Yes, in the area of chess, just in that domain, because it can apply skills in the area of playing chess. So we interact with intelligent systems. The picture on the right, just what we want is not a system that works the way we do. Have you heard of these projects? People are trying to build artificial brains. I mean, that's a fascinating project, but that's something very different than artificial intelligence, right? We know that, it's very difficult to build a brain. Why is it difficult to build a brain? Very simple reason. We don't know how the brain works. So since we don't know how this works, how are we going to build an artificial one? So you can guess from this, and you probably already know, that artificial intelligence systems don't work the way this works. They may do something that appears similar, but they don't work the same way at all, right? How old does the human have to be able to differentiate between the dogs and the muffins? Pretty young. They've got that one solved. The little humans can do that. Funny how they can do that. All right. Well, we don't need a brain. We don't need an artificial brain. What we need is systems that interact intelligently with us, right? So it's not about including AI and machine learning algorithms in systems. It's about having the systems come across as intelligent. So that's kind of a different slant. Now that may involve those technologies, that's great, but the goal is the intelligence. In fact, we may have systems that use machine learning that don't come across as very intelligent. Like my system that I said, hi, how are you, right? And it said, I don't know what you're talking about. That didn't come across as a very intelligent system to me, no matter how many great algorithms were in it, right? This is McDonald's. You have those here and everywhere, right? And do you have these kiosks yet, though? Have you are they here? Yeah? Or in Australia? Okay, yeah. So this is not just about a kiosk. This is about a whole different way that McDonald's is redesigning a restaurant. The question I have for you is this a more intelligent restaurant? Because instead of the people at the counter that sometimes misunderstand, that are hard to keep at work, that are hard to train, that are hard to retain, that maybe aren't giving my customer a very good experience because of that, versus one host who is higher level, and so forth, and the kiosks that allow me to customize my order and pick exactly what I want and so forth. Does this overall make McDonald's a more intelligent system to me, right, when I walk in the door? That's the question. Perhaps so. And other restaurants are trying this. This is a restaurant in California that's completely automated this way. No waiters at all. You interact completely with the touchscreen. And that's interesting, right? So it's a different kind of experience, right? Okay, let me go on. Somebody mentioned the automation levels from SAE for automobiles and the chauffeur. Well, this is exactly the point. There's a baseline intelligence of the driver plus car system that you have now. Let's hope, right? When you're driving your car, you plus the car are an intelligent system. You think? At least a little? Yeah. All right. So what we want to do with automation is add to that intelligence, not reduce it. Not say, can we come close to that? We want it better. The experience we want at level 5, or maybe it's level 9, is the experience of having a chauffeur. Not the experience of some technology automated thing in my car, some algorithm, but the experience of a chauffeur, that level of service, that level of assistance and so forth. Okay. So how do we start measuring intelligence? That's really the point I'm getting to today, beyond just a general notion of intelligent systems, is how do we think about intelligence? So these are some pictures that are kind of fun, right, of dogs being sort of intelligent, you might say, right? This one is getting up the fence here by wedging itself against the fence post, of the 2 dogs cooperating here. So how do we start to measure intelligence in systems? Well, can we use what we use for humans? Maybe. Can we use what we use for animals, right? Possible elements would be speech or language, although we're not there yet with computers. We're not able to interview them, question them to see how intelligent they are, and maybe that comes someday. Or animal intelligence. Can an animal understand the intent, obey something, solve some sort of problem and so forth? So how do we assess human intelligence? Well, we have primary approaches of using language and so forth. Mostly we give people intelligence tests, but have you noticed most of those intelligence tests rely on language? Now some of them don't. Some of them give you symbols, like IQ tests, right? And they don't require a particular language, and that's interesting. But then what are other elements of intelligence? Well, you think of somebody getting a Nobel Prize, You think of somebody being sort of worldly. Do you recognize the image on the right? Doctor Who, right? So somebody who has traveled widely and lived a long time and knows lots of things and can speak well. We think of that as intelligence, right? or being able to apply logic and deduction, Sherlock Holmes, right? Being able to solve mysteries, things like that. All of those are elements of intelligence. Now, can we apply those to systems? Well, not yet. Maybe in some decades we can apply that kind of standard. All of these require language. So how can we do it without language? Well, this is an interesting test. I doubt any of you have taken this. This is called the Wisconsin card sorting test. And you're given a card, and then you're given a choice of cards and the next card, and you're supposed to match this card with one of these. So just tell me, which one do I match here? This card matches which one? Depends on what? Color, number, or shape. So what do you do if you're taking this test? You have to pick. So you put it with the blue. Blue is blue. And then it tells you right or wrong. And what happens throughout this test is the rules can change. And that's part of the intelligence test, right? And there's all these statistics that come out of this about somebody taking this test. Do they recognize when the rule changes? How long does it take them to adapt to the new rule and then start playing that way, right? And this is all part of an intelligence test. It's very clever. So I think, by the way, a side research project that I think would be brilliant, and I may do it if you want to join me, let me know, is to create a neural network for the purpose of taking this test. And see how it would do. And it can have the same instructions that the human gets. It can have the rules, it can know it changes, it should get the same instructions, right? And that would be interesting. Maybe that would be an easy task, maybe not so easy. How do we test animal intelligence? Their ability to be trained to a task, do a task without preparation, like running a maze to the end, reinforcement learning, we call that in the AI world. And can we test an intelligence level by doing something like that? All right, so the characteristics of intelligence behavior, and I just listed a few that I found on the list here, is can we leverage, this is the kind of the thinking question, can we leverage these more abstract notions of intelligence to think about intelligent systems and to think about making systems more intelligent? And I think we can. How much more intelligent is an 18-year-old versus a 1-year-old? How do we quantify? See, that's difficult to quantify. You can't give them both the same test, right? But we do think the 18-year-old is more intelligent than the 1-year-old. Hopefully, right? Some of them anyways, right? In different areas, perhaps. So how do we apply these notions? This is a map of intelligence versus age based on a number of different kind of dynamics of tasks and so forth. But this may depend on bias. As we've always said, intelligence tests are biased toward the particular skills that are required to pass that test, right? Analogies or something like that. So are those fair in terms of general ideas of intelligence? All right. So I think we have to, at this point in the AI world, we have to think more about infants, how we would assess the intelligence of animals or very, very young humans, because that's the level that our AIs are at for the most part, right, in terms of general intelligence. So how do we apply those sorts of things as a way to think about how something can be? One dynamic that intrigues me is this last one. Can an AI system be trained to learn how to learn so that it becomes a more of a learning system? Yeah, thanks. And let's go on. So here's a possible research agenda, right? Something to think about as we go into this area. When we think about how humans learn something, let's say how you teach your son or daughter to play baseball or any kind of ball, right? Well, you start out by putting them on the basketball court with experienced basketball players and say, go. No, they'd be completely lost. We need to teach the young human some basic skills, throwing and catching first. You remember how you did this? Catch, oh, now you catch, now you throw it back. And we build that skill through a number of repetitions and so forth. Then on top of that, they learn aiming, right? They learn throwing, they learn other things. And eventually they can put these kind of modular or transferable skills together into a larger intelligent behavior. This typically isn't the way we're doing AI systems today. And I'm not saying it should be, but it's something we can think about. Like, are we moving towards systems of intelligent systems? So these different AIs and machine learning imagined systems that maybe each have learned a certain skill, can they be somehow combined to make a more intelligent behavior overall? And perhaps be more resilient because we're combining modules of intelligent behavior, not just some overall behavior that we've really trained on. All right. Some of these skills may be useful for games. They might be useless in cross-country skiing, though. See, we have to train a different set of fundamental skills to get someone to that. So I want to finish up here and just give you maybe a few draft principles of intelligent system design. What are some things we could think about as we're trying to make systems more intelligent? Well, the first one here, when designing conversational systems, think Play-Doh, not Plato, right? Play-Doh, you familiar with that, right? Children's buddy toy, right? The idea is there are stages that people learn language. You have language as an example here. What do I learn? If I'm going to start learning Spanish, do I start speaking the way you people speak who have grown up here? Of course not, right? I start with some very basic notions, some very basic words, and I grow in my capability in speaking Spanish until ultimately what I understand is I can start thinking in Spanish. That takes a while, doesn't it, right? Thinking in the new language. But many of you who speak multiple languages can think in different languages. And some tell me that you're a different personality. Do you notice that? Are you a slightly different person when you're thinking in one language versus another, or do you not think? What do you think? Some of you may have multiple personalities and not know it, right? Okay. So think about basic capabilities first and allowing a system to grow. Second principle, think improv, like improvisational theater, not Jeopardy. In other words, not training a system to answer very technical, specific questions, but have more general skills. One of the principles in improv theater is whatever someone gives you, you kind of go with it. You don't say no. You don't ever say no, right? You say yes, and you expand, and you're kind of generous with how you accept whatever the other player is giving you, and you create something from that. And our systems apply that idea, right? How often has a computer said to you, invalid, stop, that's it. Don't say invalid, say, I think you might be saying this. How about this? You know, have it interact a little bit like an intelligent human being. You notice, if you go to a 2-year-old human and you give them a long, complicated sentence, what will they do? Will they throw up their hands and say, I don't understand? No, they'll hear something in it and they'll kind of go with it. They'll take a word or they'll take a phrase and they'll just kind of run with it. You know, and maybe our systems need to do something like that. Next one, context is king. So the system should be aware to anthropomorphize the system. Of course, we should not anthropomorphize systems because they hate that. No? Okay. Think about that one later. All right. So the system should know its context. If I say I want a table, that's a very different thing if I'm in a restaurant or I'm in a furniture store, right? So the system should be aware of that and should be able to tailor its not only its responses, but its understanding. Or I think this last one is a good one. I'm feeling blue, how about some jazz? Well, that's a complex query, right? But should the system say, I don't understand? And I tried this, if you ask who was playing with Alexa here earlier today, right? If you give this one to Alexa, she does a really good job with it. She says, I think you'd like to hear some jazz. Well, did she, right, understand this? No. She just picked out jazz and said, jazz, music, I can play jazz, here's some jazz. You know, see, that's pretty good, that's intelligent. Without trying to be too intelligent, it just kind of went with it. It could have been wrong, you know. Maybe I needed a psychologist, not music, right? All right, last one here, or second last one. Coddle the beginner and reward the experienced user. This is a good HSI principle, right? The system should be able to take care of a beginning user, but should make it very fast and efficient for an experienced user. So many systems still fall down on that. They're one experience for everybody all the time, that's it. All right, whoops, actually didn't really hit that one. There we go. Last one, teach systems self-care. Have systems be able to maintain themselves, monitor themselves, do that. We have the horsepower, we have Moore's law, we have the computing power. Let them monitor themselves, not be so dumb about their own failing mode. So this journey is just beginning. So I hope these are some thoughts to kind of get us thinking, and we'll go on from here in INCOSE and other places.
Thank you, Barclay. Any questions for Barclay?